Well, alrighty then, ladies and gentlemen, boys and girls, everybody else. We're going to take our first crack at this flipped classroom. You watch the lecture and then come into class and we do some homework together. So we're starting out with a doozy. 2.7 is the derivatives of trigonometric functions. So we've already seen how to calculate derivatives of many of our algebraic functions, whether they be polynomials, or rational functions by way of the quotient rule. And we're feeling hopefully pretty confident, pretty comfortable with that. But a huge sector of our math lives is currently shut off to us in terms of figuring out how the trigonometric functions are changing at a given moment. Okay, because that's what the derivative tells us, is that slope of the tangent line to a curve at a given moment, going from average to instantaneous. And so we're going to focus our attention today on the trig functions and seeing if we can determine what their derivatives are. The first one is kind of going to lay the groundwork for everything else. And so the first one is sine. And what we're going to do first is we're going to use our graphing utility and we're going to plot the numerical derivative of the sine and see if that gives us any sort of hint to what that derivative should be. And I think it'll be a pretty massive hint. And then our first task together will be showing that what appears to be true is actually true. So in your y equals window, if you want to press math 8 for the numerical derivative, we want this d dx. And we're going to do the sine of x. And instead of just at a point, if we just do x here, it'll just plot the function for us, the derivative of sine, whatever it is. And then if we go to graph, very interesting. Why is this interesting? Because this curve, which is theoretically the curve of the derivative of our sine function, looks remarkably similar to the cosine. And in fact, if we wanted to plot the cosine, it would be indistinguishable. Well, that's nice. The red line is just covering up the blue line. So our intuition based on this, and this help from our technology, is that the derivative of the sine is the cosine. And it is. So we're going to go through and show that. So I'm going to give you just the theorem, and then we're going to prove it. And then that fact that the derivative of the sine is the cosine is going to be kind of the backbone of what we do moving forward to show all of the other derivatives. So 2.7.1, derivative of the sine function. Simply the derivative of the sine of x is equal to the cosine of x. Okay. I should have mentioned this at the beginning. As you're watching these, it usually works out all right to turn the speed up on the playback on YouTube to 1.25. I'll kind of start to sound like I'm talking really fast, but you should still be able to comprehend, so that you're not having to watch the full length of the video, but watching a quarter less in terms of the time. I will probably, maybe after I figure out how long this is at the end, maybe put some stopping points in for, hey, you should watch this on Monday, this on Tuesday, but for now, we're just going to charge through. So we're going to prove this. And sort of the big trick we're going to pull with this is the angle sum identity of the sine. So recall, or let's say proof. The proof here is going to start with a recollection of the sine of a plus b. Why are we doing this? Because the way we're going to prove that this is true is we're going to plug sine into the definition of the limit. And if you recall, the definition of the limit usually includes f of x plus delta x. So we need to remember how to do that with sine. And the way we do that is sine of a times cosine of b plus sine of b times cosine of a, or however you want to remember it. For the sine addition, I usually just go sine just because it makes sense to me. I think maybe in your book it has sine and cosine swapped and keeps the a's and b's in the same spot, whatever you want to do. We're going to call this equation 1. Okay. So then, with that in mind, if we allow f of x to be our sine function, then we can find the derivative of f using the definition of the derivative. In other words, that f prime of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x, all divided by delta x. Just that incrementally smaller and smaller average rate of change until eventually it becomes instantaneous when delta x is 0. Okay? Well, so now we can see, okay, that's why we're remembering this guy, because we're about to turn f of x plus delta x into the sine of x plus delta x, and we need to know how to deal with that. So this becomes the limit as delta x approaches 0 of sine of x plus delta x minus the sine of x, all divided by delta x. And now we get to apply equation 1 up here. So apply equation 1. And now this limit becomes the limit as delta x approaches 0. We're going to apply the angle sum identity to this guy with a being x and b being delta x. This will become the sine of x times the cosine of delta x plus the sine of delta x times the cosine of x, all still minus the sine of x. And still dividing by delta x. Okay. So the move from here to here is just an application of this identity. Sine of x plus delta x becomes that sum. Okay, so now we're moving in the right direction, but we need to do some finagling in order to be able to apply this limit, because we're still having some issues with this delta x in the denominator. And so I think where we're headed is we're going to end up with some trig identities, either the sine of something over that something, or maybe 1 minus cosine over that something, and then be able to apply some of these limits. And so we're going to rearrange a little bit. We're going to take this sine of x over the limit of delta x, limit as delta x approaches 0 of the sine of x times the cosine of delta x minus the sine of x plus the sine of delta x times the cosine of x, all divided by delta x. Okay. Now, I'm not going to show every last little breakdown of what's happening here, but I'm going to walk you through, and hopefully from here to the next step, we don't lose our minds. But what we're going to do is we're going to break this fraction into two different fractions, which is totally legal, okay? You can choose to divide a fraction into parts. That is fine. So I'm going to take this delta x and divide it into this difference, and then this delta x into that part of the sum. As I'm doing that, I'm also going to factor out a sine of x from this new half of our limit. Okay? So this will turn into the limit. We're going to have two limits here. We're going to have a limit of this part plus a limit of that part. So the limit of delta x, or as delta x approaches 0, this sine of x is going to get factored out, leaving us with the cosine of delta x. That sine of x was factored out with this one, minus 1, divided by delta x, plus the limit as delta x approaches 0 of the sine of x times, the sine of delta x, that's important, delta x times the cosine of normal x divided by delta x. Okay. So when we split a fraction over an addition or subtraction, both those parts get divided by the denominator. Okay. If you're not sure, just like go use some numbers off to the side and convince yourself that that's true. When we divide a product in our numerator, it only goes to 1. Okay. So because what we're about to do is now divide the delta x in both these limits just into one part of the product in the numerator, and those are going to give us some limits that we can actually evaluate. Hopefully, you can probably already see where we're headed. That's going to be a nice limit, and that's going to be a nice limit. And so we'll just write it out the way that it works for us. So this will become the limit of, delta x, as delta x approaches 0, of the cosine of delta x minus 1 over delta x times the limit as delta x approaches 0 of the sine of x, plus we do a similar thing over here, just dividing this delta x into this guy, the limit as delta x approaches 0 of the sine of delta x divided by delta x times the limit as delta x approaches 0 of the cosine of x. And this makes us happy because now with a little bit of rearrangement here, both of these limits we have identities for. And so delta x going to 0 is not an issue. On these parts of our limits, there's no delta x in here, so we don't care what it's doing. This is just, as far as we're concerned, a constant. So these two things going to 0 are just going to turn into these two functions. Okay, so the quick rearrangement we do on this guy is to factor out a -1 so that it becomes 1 minus the cosine of delta x over delta x. And then this guy, well, we'll see what that guy becomes, times the limit of sine of x as delta x approaches 0 plus this whole mess. And now we apply the limit. This is an identity, and we know that this is 0. It becomes negative 0 times the limit of sine of x as delta x goes to 0 is the sine of x, plus this limit is 1, and this limit is cosine of x. This would be the same as if this said the limit of z, the limit as z goes to 0 of cosine of x. There is no z, there is no delta x, so this just becomes what it is. Doesn't matter what this quantity is doing, it's not involved here. And so then, of course, simplifying, this first part goes to 0, and 1 times the cosine is the cosine. And so we have shown that f prime of x is in fact the cosine. And recall that f was sine, so the derivative of sine is cosine. Pretty cool. All it took was a little bit of creativity in the application of our definition of the derivative. And so this becomes immediately useful to us, as we'll see in example 1, because now we are equipped to tackle derivatives that include the sine. And that makes us happy because the sine is an important part of our mathematical journey, and we can't just run away from it every time they ask us to compute the derivative. We need to be able to handle it, and now we can handle it. So let's say we need to find f prime of x if f of x is equal to x squared times the sine of x. Before, we would run to the hills because we didn't know what the derivative of sine is, but now we do, and so we can do this. This is going to require us to use the product rule because this is x squared times the sine of x, but that's okay. So it's the first thing times the derivative of the second thing. Oh, there's an x in there. Plus the second thing times the derivative of the first thing. And now we are able to find the derivative of the second thing. And that's nice. And this turns into x squared, the derivative of sine, we now know to be the cosine. Over here, the derivative of x squared is twice x, and sine of x is just sine of x. Would you look at that? No sweat. I guess this should be example 1. So that's cool. That's fun. That's lovely. Expanding our mathematical knowledge. One trigonometric function at a time. But of course, there are a bevy of additional trig functions. Well, I don't know if a bevy. Does 5 a bevy make? Because we've still got cosine, tangent, secant, cosecant, cotangent. Ugh. Only 20% done? Yeah. Okay, but let's go. We got this. We're fine. So we're going to do kind of like the same protocol. We're going to see what it looks like. And when I say it, I mean cosine, because that's our next journey is what is the derivative of the cosine? And so going to our graphing utilities, let's just clear this out. Yeah. Again, we'll go math 8 for the numerical derivative with respect to x of the cosine of x. And we want x to equal x because we want the whole enchilada. And we press graph. And you notice it goes quite a bit slower than when we just plugged in a trig function, because at every step here, it's computing the numerical derivative. So it's kind of a longer processing deal for your calculator. Okay, so this still looks like a trig curve for sure. The question is which trig curve? Well, 0 or 0, so that feels like sine, but it's not increasing like we expect the sine function to increase. In fact, it looks kind of like the opposite of what the sine function usually does. Well, and that's because it is the opposite of the sine. In other words, if we plotted the opposite of sine, or negative sine, as you might call it, my guess is that that red line we're about to see is going to cover the blue line. But let's let the calculator do the talking. And notice how much quicker that is, because it's not calculating at every step. And there you go. So our intuition, aided by our TI-84 plus graphing utility, is saying it looks like the derivative of the cosine is the opposite of the sine, is the negative sine function. And so now we're going to use that same definition of the derivative and walk through, now aided by, or actually no, we're not going to use, I lied, we're not using the derivative of the sine. We're just going to use the definition of the derivative, say that 12 times fast, and the angle sum identity for cosine. And we're going to have a ball doing that, I hope. So here we go. I'm going to give you the definition and then we'll prove it. And the definition is exactly what we just said, 2.7.2. The derivative of the cosine function dx of cosine of x is equal to the opposite of the sine of x. Okay. And let's prove why. Okay. Proof. Take a little swig of water, get a little parched. All right. So we are again going to start this proof with a recollection. And that recollection is that the cosine of one angle plus another angle that we'll call A and B is equal, the same as cosine of A times the cosine of B minus, careful there, the sine of A times the sine of B. Okay. Hopefully that's in your noggin somewhere, and if not, it is now. So if we let, we'll change it up, maybe call it G. If we let G of X equal the cosine of X, then using that definition of the derivative, we have that G prime of X is equal to the limit as delta X approaches 0 of the cosine of X plus delta X minus the cosine of X, all divided by delta X. And again, we see that we're going to immediately apply this addition identity to this first part of our numerator. And so doing that, we get that the limit now looks like the cosine, and again, A is X, B is delta X. we get the cosine of x times the cosine of delta x minus the sine of x times the sine of delta x minus, and this is where we could lose it here, minus this part still. So this part has become this part, and then we still are subtracting the cosine of x. And we are still dividing by delta x. Okay, so take a minute there, make sure we're all on board. We're going to do a similar thing as with our previous proof. We're going to rearrange a little bit so that we start to approach a form that is better for us. And so we're going to move this negative cosine of x over here and kind of swap these two things. This will be the limit as delta x approaches 0. The cosine of x times the cosine of delta x minus the cosine of x minus the sine of x times the sine of delta x, and all of this is divided by delta x. You can almost see like this is almost a mirror image of our previous proof. Now we're going to split this fraction into two fractions, which is legal, but we just have to divide both parts by the denominator. Okay, it'll work. And so this becomes, and we're going to also factor as we do this. So a couple things happening here. We're going to get the difference of two limits here. The first one is going to be the cosine of x times the cosine of delta x minus 1. I factored out this cosine of x divided by delta x minus the limit as delta x approaches 0 of sine of x times sine of delta x, all divided by delta x. And hopefully we can now see where this is going. This has a good feeling it's going to blow up to 0 because we see this identity hiding in here that goes to 0. This looks like it's going to become the sine of x because this will go to 1. The sine of x as delta x approaches 0 is just sine of x. But then we have this opposite out here, which is where the opposite comes from. That's where we're headed. We can see the end. Let's bring it home. This will become the opposite of the limit of delta x approaching 0 of 1 minus the cosine of delta x divided by delta x times the limit as delta x approaches 0 of cosine of x minus the limit as delta x approaches 0 of sine of x times the limit as delta x approaches 0 of sine of delta x divided by delta x. Sorry, I'm getting wonky. We're okay. Deep breath. And then let's just apply these limits. We're okay. We got this. This guy becomes 0. Negative 0 is still just 0. This guy becomes the cosine of x. There is no delta x in this statement, so it just becomes what it is. Minus, same thing here. The limit of sine of x as delta x approaches 0. There is no delta x in here, so it doesn't matter that it's going to 0. This just becomes sine of x. And this is an identity that we learned back in 2.1 whatever lesson is 1. In other words, g prime of x is equal to the opposite of sine of x. Whoa. Cool, right? Yeah. And just as we were after showing the derivative of the sine, we're now equipped to tackle derivatives that include the cosine. So let's see an example of that. For example, example 2. And we are being told to find dy dx. Okay, well, what's y? Y is the sine of x divided by 1 minus twice the cosine of x, which is like kind of nasty, but we're okay because we know the quotient rule. So dy dx, the derivative of y with respect to x, is going to be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. Well, we're not so interested here in like the quotient rule as we are in applying the derivatives of the trig function. So we're not going to like expand this out. We are going to do this part. So this becomes 1 minus twice the cosine of x. The derivative of the sine we just learned is the cosine minus sine of x times, gotta be a little careful here, the derivative of 1 is 0. The derivative of negative 2 cosine of x is negative 2 times negative sine of x, which becomes positive 2 times the sine of x. Yeah, that's okay. We'll do some distributing here. To get the cosine of x minus twice cosine squared x minus twice sine squared x. I really feel like there's an identity hidden in there, so let's go find it. 1 minus 2 times the cosine of x squared. So anytime you got like cosine squared and sine squared, you really want it to be 1. So I think in here we can make that happen. So if we get the cosine of x, I'm going to factor out a negative 2 here, minus 2 times the cosine of 2x. This now becomes plus sine squared x, all divided by 1 minus twice the cosine of x squared. And yes, indeed, this is just 1. And so this derivative ends up being simply the cosine of x minus 2, all divided by 1 minus twice the cosine of x squared. Oh, fun. Whew. All right. Like this is normally the time where I would take a break in our lecture, but we're going to keep on keeping on because that's what we do here. Fins up. Okay. I'm going to let you at this point press pause and open your book and walk yourself through example 3. You're finding the third derivative of a trig looking function, but it's just you testing whether or not you can keep applying the cosine and sine definition of the derivative. I'm going to keep on powering through the remainder of our trig functions, and then we'll probably call that a day. I think that'll be a good first chunk. So again, I'm going to write this, so maybe if you didn't hear me, pause now. And look through example 3 on page is it on? It's on page 165. Seriously, pause now. Go look at it. It's fun. You'll enjoy it. Okay, well, hopefully you're back from your pause and going through example 3. We're going to figure out what the derivative of the tangent is. Well, actually, I'm going to tell you what it is, and then we're going to prove it. So that'll be fun. And kind of in all of these things we're about to do, there's like 3 things that are going to keep kind of rearing their head, or so to speak. And so we're going to start with a recollection, so many recollections in this lecture, of 3 things. 3 things, 3, yeah. 2, 1, 2, 3, yeah. Recall that the tangent of x is actually defined by the sine and the cosine, which is like kind of sneaky. It's the ratio of the sine to the cosine. Cool. Further, recall that the secant of x is likewise the ratio of 1 over the cosine of x. Kind of sneaky, it's like the reciprocal of cosine. And then finally, this should be familiar since we just used it, but the sine squared x plus cosine squared x is equal to 1. Why is this true? Unit circle, okay? It's the 2 legs of a right triangle whose radius is 1. A squared plus b squared equals c squared. Never forget that. This is not random. It comes from trigonometry. Everything comes from trigonometry. Geometry, man. Good stuff. Okay, so 2.7.3 is the derivative of the tangent function and again, we're going to format this as, I'm going to tell you what it is, and then we're going to prove it together. Or I'm going to prove it, and you're going to watch and write down, and we'll say we did it together. So the derivative of the tangent of x, and this is going to feel weird, but it's true, is secant squared x. Ugh. It is what it is. I don't make the rules. So how are we going to prove this? Well, you'll be glad to know we're not going to have to apply the definition of the derivative. We're going to just use our knowledge of what the tangent is. And now that we can do the derivatives of these guys, now we're cooking with fire. Because now the derivative, let me just write proof here. Sorry, droof, whatever. The derivative of the tangent of x, is actually the derivative of the sine of x divided by the cosine of x. Oh, not so fast, because now this is just a quotient. We know the quotient rule, and we know how to differentiate the functions involved in that quotient, sine of x and cosine of x. We'll just carefully set up our quotient rule and see what we get, and hope that it's secant squared x, or otherwise I just lied. Okay, so the quotient rule tells us it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. Okay, so far so fun. Now we can actually do these, and we're just going to do a cleanup job and make sure that we get secant squared x. So this becomes cosine of x, the derivative of sine is cosine of x, minus sine of x, the derivative of cosine of x is the opposite of sine. This is just going to work out so nicely. This is cosine squared x. Up top, we get a cosine squared x. Negative sine times negative sine is positive sine squared, all over cosine squared x. And at this juncture, I know somebody's just like jonesing to like cancel this out. No. Don't do that. What we're going to do is apply this one. And check it out. Check it out. 1, because cosine squared x plus sine squared x is 1 over cosine squared x. Well, let's just write this a little differently. This is 1 over cosine of x squared. What is 1 over cosine of x? Good thing we recollected up here. 1 over cosine of x is secant of x. And what's secant of x squared? Well, it's secant squared x. Thus, convincing ourselves that the derivative of the tangent is, in fact, the secant squared. That was a lot easier than the other proofs. That was just applying previous knowledge. Why proving stuff is useful, because then it makes showing other stuff easier. At least that's one of the reasons. Okay. So let's move on to the cotangent. Yeah. Oh yeah, we're cruising. So cotangent, I'm not going to prove for you. You're going to do it as an exercise. But it follows this format, just using the definition of the cotangent, which is, of course, the reciprocal of the tangent, otherwise known as cosine over sine. And you're just going to kind of repeat this process, but come up with something different. And the something different that you're going to come up with is laid out in 2.7.4, the derivative of the cotangent function and so dx of the cotangent of x is equal to the negative cosecant squared x. The proof you're going to do in example for exercise 1. And you'll use this as sort of a template. Just recalling that the cotangent of x and the cosine of x over the sine of x, and that the cosecant of x is the reciprocal of the sine. Mm-hmm. Okay, so hopefully you can kind of already just see same sort of idea. Mm-hmm. Okay, so now we've got 2 more, secant and cosecant, and we can do it. Basically, we're just going to use the definitions and go. Okay, so these are, second half of this lesson is pretty smooth. I had forgotten that. Now I remember.
I have.
So 2.7.5 is the derivative of the secant function. I guess we could just do the proof and see where we're going. And I'll tell you where we're going. It's always nice to know where we're going. Dx of the secant of x is equal to the secant of x times the tangent of x. Ew. That's kind of uncomfortable. That's okay. We'll get through it. The recollection we're going to do here, we already did actually, so we're going to recall again. Secant of x is the reciprocal of cosine, and then we're just going to differentiate that. So the derivative of secant of x, we're going to think of it as the derivative of the reciprocal of the cosine, and then apply the quotient rule with our newfound knowledge of the derivative of the cosine, otherwise known as the opposite of sine. Gosh, it's going to be fun. So fun. So we've got the denominator times the derivative of the numerator minus the numerator. The numerator times the derivative of the denominator. Divided by the denominator squared. Well, the derivative of 1 is 0, so that's not very interesting. Minus 1 times the derivative of cosine is the opposite of sine. Divided by cosine of x times cosine of x. Why am I writing it like that? We'll see in a second. Will we? I hope so. And so the opposite of 1 times the opposite of sine is actually just normal sine divided by cosine of x times cosine of x. Why are we writing it like this? Well, because now, in fact, let's just keep this 1 out here. We're going to write this as 1 over the cosine of x times sine of x over cosine of x. Well, what's 1 over the cosine of x but the secant of x? And what's the sine of x divided by the cosine of x but the tangent of x? And so we have shown that the derivative of the secant is the secant times the tangent. Well, pretty cool. And then the final one, we're going to do a similar deal, and I'm not going to prove it. But if you followed this proof, you should be able to do it. And in fact, I will ask you to do it on one of your homework exercises. And what it is 2.7.6, which is the derivative of the cosecant. So dx of the cosecant of x is equal to the opposite of the cosecant of x times the cotangent of x. And again, I'm going to leave it to you in exercise 2. But the idea is simple. You're going to differentiate one over the sine of x, because 1 over the sine of x is, of course, the cosecant. And applying the product rule to this should yield that if you do some trickeration, as we did with the proof of the derivative of the secant. I think that's a good stopping point. I feel like I've been talking for a while. And there is still a little bit left of this lesson. We will basically look at using this now, what we just went over, to verify what the graphs of, of what the graphs of your trig functions actually look like. Because though you think you know, you don't really know. We've sort of just used intuition of what the trig functions are doing, but now we'll be able to use calculus to actually verify that what we thought the curves were are actually what they are. That'll be fun. And that will be our next lecture together. I'm going to figure out how to stop the recording.